Okay, now, so basically the question was, that this sphere is submerged 25% in water, and you had to find out the density of the sphere, and it was in equilibrium. The sphere is now held so that the entire volume is below the surface of the water. Okay, so that means V naught is equal to Vf, right? Which means all of it is submerged. Okay. The sphere is then released. Okay. So calculate the initial acceleration. Okay, so the weight of the ball, weight was equal to rho naught into V naught into G. And we figured what that out was. So 263 into V naught is what? What is V naught? Did we know V naught? V naught, V naught. Okay, we don't know what that is. That's a problem. Okay, but that's fine. V naught into 9.81. Okay. Over the upthrust is also rho fluid into volume of fluid displaced into G, which was density of the, okay, so 1050 into, by the way, you can clearly tell that because this is the ball is much less denser than the water. So it's clearly going to rise. We already know that. So that means going to accelerate upwards. So it's kind of like you push it down in the water. Okay, so 1050 times Vf, I don't know what Vf is, but it's just the same as V naught in this case into 9.81. Okay, now, how do I find out the acceleration? Acceleration is, you pretty much always use the resultant forces if forces are involved. So resultant force is equals to mass into acceleration. What is the resultant force? Resultant force is just the difference between them. And you know that it's going to be F upthrust minus weight because it's going to accelerate upwards, right? Everything else is the same. The only thing is different is 1050. The only thing that's different is 1050 and 263. V naught is same, 9.81 is same. Acceleration will be upwards. The resultant force is, so 1050 into V naught into 9.81 minus 263 into V naught into 9.81. Okay, this is the result force equal to mass uh, into acceleration. Okay. So the problem is I have two unknowns. I have mass unknown and I have V naught unknown. Let's take everything else as common. As I take V naught as common, then that leaves me with 1050 into 9.81 minus 263 into 9.81 equal to mass into acceleration, right? So we want to find out the acceleration. Okay. Hmm. How to find out the acceleration now? Let's find out this expression first. Did any of you solve it first? 1050. Yes, Kaima. Are you here? 260.
Yes.
Have you solved this before? 1050 into 9. This is 7720. Okay. Yes, Abhi, any ideas?
No, I really didn't solve it.
Okay. So the problem is now we've got like I have got three unknowns. I don't know what V naught is, I don't know what M is, and I don't know what A is. Okay. Yes, Abhi, Hania, any idea?
No, not really, but like we have mass
Hmm.
and volume, so can't we like plug them
Ah,
together and like get the density?
exactly. We know the density of the ball. Density is mass over volume, right? So that means if you have, if you were to divide this on the other side, then isn't this basically density, right? So 7720, that's exactly what you've got to figure out. 7720 is equals to density of the ball times acceleration, right? And we already know what the density of the ball was, 263. So 7720 divided by 263 is equal to acceleration. That's it, right? So whenever you see familiar, variables, that's absolutely what you've got to do. You've got to connect them together, and you've got the answer. Voila. So 29.3 or 29.4 meters per second is the initial acceleration. Okay. Okay. So always try to make an expression, regardless of whether you know the variable or not. sometimes, you might uh, get it cancelled out at the end, and it will be very satisfying when that happens. Okay. Now, the question says the sphere accelerates upwards but remains entirely below the surface of the water. Okay. State and explain what happens to the acceleration of the sphere uh, as its velocity begins to increase. Now this is a good question. State what happens to the acceleration of the sphere as its velocity begins to increase. Okay, wait. The sphere but remains entirely below the surface of the water. Okay. So if the spheres, okay, if it remains below the water, that means that hmm, it was happening to the as its velocity begin to. Okay. So there are only two forces. The weight is not going to change, but the upthrust is going to change, right? So this is what happens to the acceleration. Hmm, good question. Try to think about it and come up with an answer. You've got like, I'll give you 2 to 3 minutes. This is very similar to the examples that we did in our previous examples, where I said that if you have too much of the difference in forces. Yes, Aris, any ideas? What's going to happen?
Would it like? I'm not sure.
Hmm.
I don't know.
Hmm. Okay.
Would it remain this? Would the acceleration remain decrease as the depth is decreasing?
Yes, that is true. Acceleration will fall. But why will it fall? Because it says that the sphere accelerates upwards but remains entirely below the surface of the water, right? That means
Yeah.
that the volume submerged is the same. Volume submerged is the same, right? So that means it's neither weight that falls, neither the upthrust, right? So what are the components of weight? Density of ball, volume of ball, and G. And what are the components of upthrust? Density of fluid, volume of fluid submerged or displaced into G, right? By saying this statement, he has clarified that neither volume changes for anything. So it's neither one of them that changes. First of all, neither weight nor upthrust changes. Upthrust changes because there's nothing changing from them, right? Because of this statement, they've clearly said that upthrust remains the same. Because if for example, if for example, the ball were to start here, right, and it reached over here, right? Now, because of that, the volume of the liquid displaced is going to come down as well, right? So clearly, in that way, the upthrust is going to fall. But in this example, he says that the sphere remains entirely below the surface of the water, right? This is slightly different to the example that we did over here. That if, for example, if the F upthrust is too high, right, then the block is going to rise and reduce the volume that was, immersed, to reduce the F upthrust on it, right? Because right now it's upwards 22 newtons, downwards to 20 newtons. Now, because there is an upwards resultant force, the block is going to rise, right, to reduce the volume of the object that was submerged. And then, again, at some point, upthrust is equal to the weight again. Okay. So, of course, we reduce the upthrust by reducing the volume of the object submerged. It rose a little bit to the top. But in this example, they've already clearly stated that it remains entirely below the surface of the water. So upthrust is not changing. Okay. So the answer to this question is neither W nor F upthrust changes, since volume, it's a 3-mark question, volume of object submerged does not change. Okay. Now this is only like 1 mark, but because they've got asked you to explain. Okay. What's going to happen is, do you remember that in all fluids, we have something called the drag force, right? And we have that, what that drag force is called in air is air resistance. So if you have air resistance in air, doesn't that mean you will have fluid resistance in liquid as well, right? So if the ball is trying to accelerate upwards, then that means acceleration upwards, then that means there is going to be a downward force, which is called drag force as well. Let's call this F drag, right? Now, this is exactly like air resistance. What's going to happen as as you reach to the top, drag force is going to increase. As velocity increases, drag force, this is also called the viscous force in liquids, by the way. The viscous force, right? If you try to move around in a swimming pool, there's going to be a drag force in all directions. If you try to accelerate in any direction, it's going to push you back, just like air resistance, right? Viscous force. If you try to move in ketchup, right? If you're like in a swimming pool of ketchup, then it's going to be extremely difficult for you to move because it is so dense, right? Upthrust is different than viscous force, by the way, because upthrust is always upwards, right? It's always trying to bring to the surface. Drag force is in every direction, just like air resistance. You try to move in any direction, drag force is going to push you away. So drag force pulls you down. Okay. And this is just like the terminal velocity question. And as velocity increases, no, wait, I've already written that. As velocity increases, drag force increases, pulls you down, and reduces upward net force. Thus, acceleration also falls. Okay, so that's how you solve this. Any questions? All good? Yes, Aris, did you get it?
Yeah.
Yes, Abhiya? Understood? Or
Yeah.
no? Okay. Okay, let's move on. Next question. Okay, now this is a really good question. This is one of my favorite questions because this is going to ask you to smartly use vectors to figure out what this, what they're asking for. Okay, just for the first part, for the 2 marks. Okay, read the question carefully and try to figure out what they're saying and what to do. They've given you a lot of information, like not even a little bit. They've given you a lot of information, and it's very confusing what to do with information. Okay, so a lot of information is not important. The important thing is how you're able to use that pieces of information and build and solve the puzzle with it. Okay, so the more the more the pieces of the puzzle, the more difficult it is going to be to solve it, right? But of course, it's also going to be much more satisfying when you build it. Okay, I'll give you 5 minutes. Try to think about what the question is saying and how to figure it out. Okay. I would like to have answers from all of you to see, where you went wrong so we can see what's the alternative. Okay. Yes, Abiha, what did you get? Did you get an answer?
I got a 267. I'm not sure because I think the value
Okay,
is a bit
that's
too
fine.
high.
That's fine. What did you get? 67?
267.
267. Okay, okay, could be right. Okay, yes, Kaima, what did you get?
I also got 267 answer.
Okay, Hania, what about you? What did you get?
Yeah, I got 267 too.
Okay, Ares, what did you get?
I don't know why, but I got 227 instead.
27. Okay, let's see. I'm not sure if 267 or whatever that was right is the right answer. Now, l- if you read the question, you see that this ball is already attached to the bottom of the river, and it's like flowing towards the right. Okay, because it's the direction of the flow water, and it's attached with a wire. Okay, and it says it's fully submerged and in equilibrium, so that means the resultant force is equal to zero. With the wire at an angle of 68 degree to the horizontal, the weight is 32 newtons. Okay, that means the weight of the ball is 32 newtons. Okay, the upthrust that is acting on the ball is 280 newtons. Okay, but there is a very, very big component of tension as well, right? Tension is in this direction. Tension is in this direction. So tension is pulling the ball like this, right? Because if there was no tension, then the ball would just fly away. Okay. Now you could break the tension into two. Oh, by the way, there's another force. There's another force in this direction, F, right? And that is the direction of the flow of water. Okay. Assume that the force on the sphere due to the water is in a horizontal direction. Okay. Right? So the force due to water is towards the right. Okay. Now let's draw the ball over here. If you draw the ball over here, right, there is a downward force W. There is an upward force. So what was W? W is 32 Newton. And there was a upward force of 280 Newton. And there is a rightward force of F. We don't know what that is, which is equal to. Now, tension is in this direction, right? So tension is in this direction. But you can break it into components, right? So if this is 68 degrees, right? Doesn't that mean that, so what is this angle? So if that is 68 degrees, then that would mean that this angle is also 68 degrees, right? It makes a Z. This must also be 68 degrees, right? And if you have that angle, then it's just a composition of the vectors. So if this is also 68 degrees, this is 68 degrees, then that means that this is going to be, uh, okay. So this vector is going to be t sine 68. No, it's going to be t cos 68 with the angle. Okay. And there's going to be a vertical component, and that vertical component is going to be what? It's going to be t. It's going to be t sine 68. Okay. Now the question said that the question is in equilibrium. Determine the tension. Find out what t is. We know that because it is in equilibrium, the resultant force is zero, but not in just one direction, in all directions, right? And you could find out pretty easily from this vertical, component. So you know that 280 Newton should equal to 32 plus t sine 68, right? So you've got to be careful. So that means 280 minus 32, okay, equal to t sine 68. And then 280 minus 32 divided by sine 68 is equal to t. And there it is. You could not have solved it using the horizontal components because you neither know what t is, you neither know what f is, right? So it was not solvable. You could find out now what f is if you have t, but you cannot find out, this first question using the horizontal components. So 280 minus 32 divided by sine 68. So that is right. So that is 276. 276. That's right. Moving on. Next question. So for the sphere, calculate the volume. Now, how do you calculate the volume of the sphere? Now, I think that you could pretty easily do it by multiple methods, I believe. So if you have density of object is equals to mass over volume, do you know what the density of the ball is? No, you don't. Okay. Okay, pretty simple. You can just use the formula for upthrust. F upthrust is equals to density of density of the fluid multiply volume of the object submerged or the volume of fluid displaced into G. We know what the upthrust is. It's 280 Newton. And be careful to use the density of the fluid over here, right? Because that's what the formula is, because of the fluid. What is the density of the fluid? That was given. Water is given. 1 into 10 power 3. And Vf is what we want to find out, and into G, right? So you divide G on the other side, divided by into G. Okay, great. So what does that turn out to? So Vf is equals to 280 divided by 1 into 10 power 3 into 9.81. So that is 0.0285. 285. Great. Okay. Now, what is the density of the ball? Now, this is a good question. How do you find out the density of the ball, right? Because in the earlier question, you used the density of the fluid displaced, right? But to find out the density of the ball, you just simply have to do what? You know that weight is equals to density of object into volume of object into G. You know what the weight is? It's pretty simple. The weight was 32 Newton. Okay, equal to density is what we want to find out. Into volume, we literally found that out in the above part, 0.0285 into 9.81, right? So that means 32 divided by 0.0285 into 9.81 equal to the density of the object. That's it, right? So you've got to be careful. That's why, I always write down very clearly what the subscripts are for every one of those formulas, because the single most confusing thing in all of upthrust and, all upthrust and buoyancy and Archimedes principles, it's the subscripts, right? We don't know which formula to use where, and uh, what is the component of one of those formulas. Are we to use the density of the object, the ball, right? So the only most important thing is that in the upthrust formula, this V is the volume of fluid displaced, or it is equal to the volume of object submerged. They're both equal if they're all they're both equal in this case. If, for example, 5 centimeter cube of volume was displaced, then that must mean the object that was submerged is also 5 centimeter cube, right? But submerged, not the total, right? If, for example, only this much was submerged, then that's the number that's going to show up in the formula. Okay, right? So we figured out the answer. That was 32 divided by 0.0285 into 9.81. Yes, questions. Bring it on. 114.5. Yes, Ariz, Hania, Kaima, Abiha. Bring in questions. Anything confused? Brain work? No? Hmm. Yes, should we move on to the next question? Or no? Yes, Abiha. Make sense? Hania?
Yeah.
Okay, Ariz, should we move on to
Yes.
next question?
Yeah.
Yes, okay. Kaima, any questions? Anything confusing?
No.
Okay. Okay, let's check this question out. Uh, wait. Okay, so a spring balance is used to weigh a cylinder that is immersed in oil. Okay, Interesting. The reading on the spring balance is 4.8 Newton. Okay. So that means that okay, let's see the rest. The length of the cylinder is 5 centimeter and the cross-section area is 13 centimeters square. The weight of the cylinder is 5.3 Newton. The cylinder is in equilibrium when it is immersed in the oil. The cylinder is in equilibrium when it is immersed in the oil. Okay. Explain these terms in terms of the forces acting on the cylinder. The cylinder is in equilibrium. Explain this term in the forces acting on the cylinder. Wait, what? The cylinder is in equilibrium when it is immersed in. Okay, okay. So basically, there are uh, three forces acting over here. Three? Yep, three. Yes, Aris, can you tell me what those three are? What three forces are acting over here?
I mean, one of the forces is the weight.
Yes, absolutely. The weight of the cylinder.
The there would also be like the upthrust.
Yes, it's a fluid. So there would also be upthrust. Okay. But there is another one. What is that? What do you think? Yes, Anya. Any idea what is the other force?
Is it the drag force?
It's not moving. If it was moving, then yes, it's
Is
an equilibrium.
it tension in the wire?
Yes, absolutely, because that's what's holding the block in air, right? In the liquid. If there was no tension, then it would probably just fall down or, come to the top. So there's another force, which is tension. Okay. So the reading on the spring balance is 4.8 Newton. And the length of the cylinder is 5 centimeter and the cross section area of this, okay. The weight of the cylinder is 5.3. The cylinder is in equilibrium when it is immersed in the oil. Okay. Explain this in terms of the forces acting on the cylinder. That means that the weight must have been equal to the F upthrust plus the tension. That's it. The downward forces must equal to the upward forces. Okay. The question is calculate the density of the oil. That's such a big demand. This is uh this is one of those questions where you need to know, I do not make you do the derivations for absolutely no point. This is where it's going to be applied. This is where you're going to need to find out, you might have to derive the upthrust formula. You might have to, not necessarily. Okay. So try to figure out what this is. You don't even know, you only know, so basically you know what weight is, which is 5.3 Newton. You know what the tension is, 4.8 Newton. You don't know what the upthrust is. Okay. And that's probably the key to your answer. You have a lot of, you'll have a lot of information. You know that the length of the cylinder is 5 centimeter, and you know that the length is 5, and this cross section area is 13 centimeters square. Okay. This is a 3-mark question, but I think this should be like a 4-mark question. Cambridge is being brutal. This is supposed to be a 4-mark question. Okay.
Wait, so it's
Yes.
completely in equilibrium even in this part, right?
Yes. 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 They've shown it. They've told you that it's in equilibrium. Okay. Try to figure it out. I'll give you 5 minutes and we'll see what we can figure out after that. Very important question. If you can do this, then that means you've worked through the derivations of upthrust in the right manner, and you should be easily be able to solve this up till now. We have how many more questions? Okay. I think this is just one question. Okay. Yes, Abiha, have you solved it? Have you got
Yeah,
an answer?
but I don't
What
think
did
my
you get?
answer's it's like
Okay.
it's a bit unrealistic.
What is it?
It's like almost 8,000.
8,000? That's okay. It might be right. Might be right. Oh, by the way, I don't know if you guys noticed, all the readings are in centimeters, so be careful about that if you haven't seen that. Okay, 8,000. 8,000 is okay. That's fine. Metals have a fairly high density in 3,000, 5,000, 6,000, maybe 8,000 as well. Spring barrel super cylinder. Okay. Yes, Hania, what did you get?
I don't think mine is correct either, but I got
What?
784.
784. Okay, that might be right. RS, what did you get?
I mean, I was still doing it, but
Okay. Okay. Kaima, what did you get? Any answer yet?
I'm still not done.
Okay.
yeah, my answer is like not correct at all. It's like I got
What
5.
is it? Five. Nice. Even paper is denser than this. Five. Okay. Great. Okay, let's solve it. How to solve this question? Tough question. Okay, so at the moment, let's make the cylinder first. So this is the cylinder, and okay, this is the cylinder, and they've said to me that the weight of the uh 1 second, let me think about it. So tension plus F upthrust. Okay, weight is 5.3 Newton, and you have two forces acting upwards. So one of them is the upthrust. So upthrust is unknown. Okay, but I do know what the tension value is. So tension value is 4.8. 4.8 Newton is equal to the tension. Okay, sounds good. Hmm, sounds good. Oh, wait 1 second. Okay, okay, sounds good. So, uh, we know that the weight is equals to the F upthrust plus the tension, right? That's what the expression is. So 5.3 Newton equals to 4.8 Newton, right? Plus upthrust, right? Doesn't that mean that upthrust is 5.3 Newton minus 4.8 Newton, right? So if F upthrust is this value, so 5.3 minus 4, oh, right, that's just 0.5. 0.5 Newton is the upthrust. Now, we know that F upthrust is basically just equal to the density of the fluid multiplied by volume of the fluid displaced or of the object submerged into G, right? Now, if this is 0.5 Newton, do we have the density of the oil? No, that's exactly what we want to calculate. Density of fluid. Okay, into what is the volume of the fluid? Isn't that pretty easy to calculate? You have the area. Area is 13 centimeters square. What is the length of the cylinder? Length is uh 13. No, 5. Length is 13 centimeter. And isn't the volume of a sphere, volume of anything is basically just area multiplied by height. What is the area of the cylinder? 13 centimeters square. Okay. Multiplied by the height, which is 5 centimeter. Okay, let's see. So 13 into 5 is 65, right? So 65 centimeter cube. But this is centimeter cubed. You do not want your answer in cubes. Sorry, you do not want it in centimeter cube. Okay, now centimeter cube basically means that it is basically 65 centimeter multiplied by centimeter multiplied by centimeter, right? You want to convert it into meter cube. So doesn't centi really mean into 10 is power minus 2 into 10 is power minus 2 into 10 is power minus 2 meter cube, right? I basically multiplied all the centis together and the meter cube together. And isn't this minus 2 minus 2 minus 2 minus 2? This becomes 75 into 10 is power minus 6 meter cube. Okay, so you've got to convert that. So centimeter cube to meter cube, you convert every single one of those centis individually to get the required answer in meter cube, because density is also in meter cube. Okay. 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 So that's it. That's the volume. That is the volume. And you figure it out. The volume is 65 into 10 is power minus 6 multiplied by 9.81. That's it. You've solved it. So 0.5 divided by 65 into 10 is power minus 6 multiplied by 9.81 equal to density of the fluid. That's it. Let's see who's going to win. 65 into 10 is power minus 6. 784. Nice. Hania, you got it right. 784 is the right answer. Congratulations, Hania. You are now the best physicist among us, including me. Yes, Hania, is that how you did it? Or did you get it by luck?
No, I think I use like how you know we derivated the formula.
Hmm.
That's how I
Okay.
did it. Like how
Ah,
like I used force over area, and
okay.
then yeah, so I kind of did it indirectly. I didn't just use the
Ah,
formula.
I see, I see, I see. So yeah, you could have done it that way as well. Okay. But I saw a much neater and cleaner way, because I was thinking, why did they make us do this? Right? There was a point in making us do this. You have the weight and the upthrust. Sorry, you have the weight and the tension, so you can pretty easily calculate the upthrust from this value. So that means you can calculate it, using that very simple measurement. Okay. You could do it with the. So how would you do it with that way? So how would you do it using the derivation? So we know that upthrust is basically, so basically you found out 0.5 Newton using using the derivation. Okay, let's see if we can do that using this way though. So F upthrust is basically, we know that it at the end it boils down to uh, you know density of fluid into G times A into H2 minus H1, right? In the derivation. And that's it. So wait.
I didn't find the upthrust using the derivation. I mean like the
Okay.
whole question, the density specifically. I
Uh-huh.
use like force over area is equals to like density times G times
Okay.
H. And then yeah,
Okay.
I that's
Okay.
how I
Interesting.
found the density.
Interesting. Do send me your solution after class. I'll check it out and see how you did it. I'm interested. Curious how you did it that way. Okay. Sounds good. You got the right answer by the long method. What more could you want? Although, no, of course, that's not what you want to do in the exam. In the exam, look for ways, shortcuts to solve the exam, because in the exam, you won't have unlimited time, right? Right now, I'm giving you lots of time, but in the exam, you will not have a lot. Okay. And generally, if the number of marks is very closely related to the time it should take you. So if you've got 3 marks for the question, right? If you got 3 marks, then that would mean that you've got to accordingly spend your time. 3 minutes is more than enough. If it's taking you more than 3 minutes, that means you haven't practiced enough. If you're done within 3 minutes, that's great. Okay, I believe, uh, yeah, in some questions you might not take a lot of time, right? But in the big questions, try to solve it as quickly as you can. Okay, sounds good. Let's do this question. This is a good one. Okay, state what is meant by the center of gravity of an object. The point at which all the weight of the object all the weight of the object can be assumed to be acting. Okay, sounds good. So that means they're probably going to use this example somewhere in the end. A non-uniform rod XY is pivoted at point P. Non-uniform means it's not acting at the center. The rod has a length of 4 meters and a weight of 44 newtons. The center of gravity is 1% from the end X. Point P is okay. The sphere hangs by a wire from end Y of the rod. Okay. The weight of the sphere is 3 newtons. The weight of the wire is negligible. Force F is applied vertically downwards at end X so that the horizontal rod is in equilibrium. So that the horizontal rod is in equilibrium. Where is the horizontal rod? Okay, this is the rod. Okay, by taking moments about point P, calculate F. Calculate F. So, in moments, always try to understand what the expression is first. So, try to visualize it. So, this is the rod, and try. Oh, so first, what you should do is take the pivot and try to remove all the objects and see where would the rod pivot, right? And keep adding the objects one by one to see where would what would be the effect of that force, right? So, if this is the rod, right, and if I remove 4s and the sphere, then because there's too much weight on one side, then that means the rod is going to tilt like this. So that means this is going to provide a clockwise moment. And so is the sphere. The sphere is so further apart, so further away, it's going to provide a very strong clockwise moment. And force F, it's going to make the bar turn like this. So that means that is going to make the bar turn anti-clockwise. Okay. Now, by taking moments about point P, calculate F. Pretty simple. So, sum of anti-clockwise moment equal to sum of clockwise moment. Okay. Anti-clockwise moments are, so F into 1.1 equal to, and clockwise moments are 44 times. Okay, so 1.7 minus 1.1. So 0.6 meters plus, okay, so this is going to be 4 minus 0.6 because we figured out this was 0.6. 4 minus 0.6, so 3.4. So 3 into 3.4. Right now, this is pretty easy. This is such a piece of cake. Since some 3 marks, they will, they will torture us and make us want to kill ourselves. But in some questions, it's going to be so easy. Plus, but they will not leave you. It's very likely that in this paper, May, June 2022, there was another very difficult question that, took out the soul of you. Okay, so 3 into 34, so divided by 1.1. 1.1. The general paper pattern is that 20% of the paper is easy. Like, it's like if you have like even read through the syllabus and you've got like a basic amount of physics understanding, 20% could be solved, provided that, you've at least read the definitions and you've, solved a fair bit of examples and you've revised a little bit. You will very easily be able to do it. Okay, just kind of like this. This is the easy part. And you will see like these kinds of parts in every single question. 60% of the paper is medium, right? And this question is one of them. This is like one of those medium questions that don't require a lot of effort, but they're also, high in the number of marks. Okay. Now, 15% of the paper is hard. Okay. 15% of the paper is hard, which means that, this is one of those hard questions. Okay. Now, this was hard, but not extremely hard if you have like studied enough. But there are going to be some questions, 5%, which are going to be distinction level questions. Distinction level questions, right? And this is the one that you get only if you like solve like 20 to 25 past papers for every single topic, and you've learned through your mistakes and every single thing of the syllabus. So this is the goal Okay. The goal is to solve as much of these as possible, and I make you go through all the distinction level questions in all of the chapters as well, because once you know the distinction level questions, right, you are well equipped to solve, you are very well equipped to solve the remaining 95% of questions, right? It's kind of like, I make you lift all the very heavy dumbbells. So in the exam, the lighter dumbbells seem very, very light to you. Okay. The distinction level questions, of course, they take a lot of time in the exam, and they're like just like not worth doing it. Of course, uh, if someone can do it, of course that's excellent, that's why they get a distinction, right? But generally the distinction level questions in the exam take too long, and if it feels like it's going to require a long derivation, always leave it at the end. Okay, and do the rest of the 95%, because if you can do the 95% right, that's more than enough. Okay, and then if you have spare time, then go for that question. Okay, but this is only for the day of the exam, not for the practice. For practice, before the exam, I'm going to give you as many distinction level questions as possible, so that these questions, the rest of them, will become a piece of cake for you. Just like this question. This is like a fairly average question, or a slightly harder question for people who have not studied enough, or have, barely done any questions. But because you've solved so many difficult questions, this is just like, you could do this in your sleep, right? Okay. Let's see. So that was 44 into 0.6 plus 3 into 3.34, 3.4 over 1.1. So 33.3. Okay. By taking notes about P, calculate F, right? That was the question, right? 44 into 0.6 and, oh wait, 1 second. F is 1.1. Yep, it is 1.1. Okay, okay. Calculate the force exerted on the rod by the pivot. On the rod by the pivot. Okay. So, any idea what that's going to be? Question is in front of you. So, one more question. Yes. Any idea what's the answer? It's a very simple one. The rod is in equilibrium. Yes, Abiha. Any ideas?
Uh, like, do you
Hmm.
just like add all of the forces that are going downwards?
Absolutely. That's it. Because if you remember the conditions for equilibrium, there were two. One, net force is equal to zero, and then net moment is also equal to zero. Net moment is equal to zero, right? So net force is zero and net moment is zero, right? So clockwise moment equal to anti-clockwise. That's a given according to this question, right? But it also means that the net forces is zero. That means up forces equal to down forces and right forces equal to left forces. That's what it means, right? So what are all of the downward forces on the rod? F, 44 and 33, right? So that means the rod, sorry, the pivot is going to provide an equal and opposite force in the other direction, right? To make sure that the rod stays here, because if there is too much force downwards, right, then what's going to happen? Then what's going to happen is that the pivot is not going to hold the bar. The bar is probably going to fall down, right? It's too heavy. It's going to break the pivot. Okay. So that means 33.3 plus 44 plus 3. So what does that turn out to? So 44 plus 33. So that's what, 77? 44 plus 30. So that's roughly 80. Let's see what it is actually. Yep, it is. No, it is slightly higher. It is 81.3. Okay. The sphere in B is now immersed in a liquid in a container. Ah, they've merged it with upthrust. And you will see a lot of questions of moments that are merged with upthrust. The density of the liquid is 1100 kg per meter cube. Okay. The density of the liquid is 1100 kg per meter cube. And the upthrust acting on the sphere due to the liquid is 2. Oh, they've already given that as well. So the density of the liquid is the, wait. Now here it is, Archimedes principle. They've asked you straight up to use it. Wait. Uh, 1 second. Good question. Okay, the upthrust is, it is now 2.5 Newton. And we already knew what the weight of the block was. It is 3 Newton. Okay. Use Archimedes' principle to determine the radius r of the sphere. Oh my god. The radius r. Oh, okay. Okay, this seems too difficult. I should just go to sleep. Okay. Now, if you think about this question, initially the rod was in equilibrium, right? Because all the forces that want to make you turn clockwise are now equal to all the forces that make you want to turn anti-clockwise, right? But if you use a liquid to cushion the weight of the sphere, right? Then it's going to cancel out some of the effective force of the sphere, right? Because because upthrust is going to reduce the effective weight of the ball. Right now, if without the liquid, the sphere is just hanging and it's causing an effective force of 3 Newton, and 3 Newton multiplied by whatever that distance was is equal to the moment. But now, because you have reduced the weight of the sphere by putting it in a liquid, right? You've reduced the effective weight because it's being cushioned, right? It's kind of like, you're holding the ball in your hand. And if you're holding it in your hand, that means then it might mean that the anti-clockwise moments are now too great, right? So the rod pivots like this because the sphere is not available to bring it back down. Okay. So they've even told you over here that the magnitude of F is unchanged so that the horizontal rod is not in equilibrium. That's very important, right? That means that now, that might mean that anti-clockwise moments are now greater than all the clockwise moments, right? Because you cushioned the effect of the what is it? The effect of the sphere. Okay. Archimedes principle. We know that Archimedes principle said that the weight of, or Archimedes principle just upthrust, that of F upthrust is equals to rho is density of the fluid multiplied by volume of fluid displaced or object into G. Okay. So we know what the density of the object is. We know that it is 1100. No, that's liquid. 1100 into VF into 9.81. What is the upthrust? We already know that. What is it? It's 2.5. Okay, then this is easy. So 2.5 divided by 1100 into 9.81. That's it. What? Not all of it. 2.5 divided by 1100 into RS. Do you know what the radius of the sphere is? Or do you know what the formula is for volume of sphere? 2.31 into 10 raised to power minus 4 meter cube. The volume of a sphere, this is the most important volume you want to learn. Okay, volume of sphere and volume of cylinder, two most important ones. Okay, so volume of a sphere is 4 over 3 pi r cube. Pi r cube. Okay, now if you know what the volume of the sphere is, 2.31 into 10 to the power minus 4. I take 3 on the other side, divide by 4 over here, and by pi as well, equal to r cube. I take a cube root on both sides. I take a cube root on both sides to cancel out the r cube is equal to this value. So r radius of the sphere is equal to this expression. I'm such a pro at this. I should think of becoming a teacher. 2.31 into 10 to the power minus 4 into 3. 4 pi. So this is 0.038. So that's the radius of the sphere. Great. Okay. Now calculate the magnitude and direction of the resultant moment of the forces on the rod about P. So basically now basically what you want to do is, now the clockwise moment is not equal to the anti-clockwise moment, right? And that means that one of the moments is higher than the other, right? So it's either that the clockwise moment is higher or anti-clockwise is higher. It's very likely that anti-clockwise is higher. Why? Because you've cushioned the effect of the weight of the sphere. So it's probably that the clockwise moments are not enough to keep it balanced. Okay. And now they're asking you, what is the resultant moment and in which direction? Okay. And I'm going to leave this question to you. I will wait for you to solve it. This is the last question we've got for today. And so this force was, by the way, 33.3 Newton. So this was 33.3 Newton unchanged. Okay. And I'll give you the distance as well. This was 0.6. Okay. And the total distance for the rod till the sphere was 3.4, right? So this is a 3.4. This is 3.4 and 33.3 was 1.1. Okay. I've given you all the information. Let me know what the answer is. If all of you get the same answer, then that must be right. It's a simple one. Okay. I'm waiting for you to solve it and I'll be back. Yes, Aris, did you get it answer? Simple calculation, that's it.
I'm done calculating. I'm almost
Done.
done
What did you
calculating.
get? So resultant moment is?
I'm almost done calculating it. Just give me
Okay,
a
okay.
second.
So all you had to do was find out anti-clockwise moments and the clockwise moment. Right? So what are the clockwise moments? So the clockwise moments are the weight of the rod, sorry, weight of the sphere, effective weight of the sphere. Effective weight is now different. Why? Because initially it was 3 newtons, but now there's an upward force of 2.5 newtons as well, right? So effective weight is only 0.5 multiplied by 3.4
I
plus
got the
the,
resultant moment as 8.2 newtons, and then that's in the anti-clockwise direction.
okay, let's see. So 0.5 into 3.4 plus 44 into 0.6. So 28.1 Newton meter is clockwise, and the anti-clockwise moment is still the same. That is 33.3 Newton multiplied by 1.1. 33.3 into 1.1, which is 36.63, right? So clearly we can see that anti-clockwise moment is greater than clockwise. 36 minus 28.1, which is equals to 8.53. 8.53 Newton meter is the answer. Direction of resultant moment is anti-clockwise. Why? Because it's the net effect is that the rod is going to turn anti-clockwise because the anti-clockwise moment is now too great. Before the sphere was immersed, then the weight of the sphere was more effective, and the clockwise moment was balancing out with the anti-clockwise. Okay, and that's it. We are done with this chapter of forces, density, and pressure. Any questions? All good? So, big, not exactly a big chapter, but a lot of tough questions from this chapter. Okay, sounds good. Then that'll be all for today. And I'm also going to send you a worksheet every week, okay, of like 8 to 9 questions of the chapters that we do, so that I know that you're solving tough questions of my choice. I'll send you a booklet as well, or if you want to, if you already have a booklet, that's fine. But I want at least like solve 9 to 10 questions every week from you, so I know that you're practicing and not just just listen, blindly listening in class, because you cannot learn physics without practicing. It's not possible. Okay, right now, if I am doing the questions, only I am learning. That's why I make you do the questions as well, right? So you learn as well. Okay, best way to learn physics is to learn from mistakes. And the only way to learn from mistakes is if you do a lot of mistakes. And you can only make a lot of mistakes if you only do a lot of questions, right? So first, do a lot of questions. Naturally, you're going to get a lot of mistakes. Then learn from those mistakes. And if you do that process, you can just like, uh, 1 second. If you do that process, you won't just be able to, get a good grade in physics. You will be able to do absolutely anything you want ever. That applies for, sports, that applies for, physical performance, mental performance, games. It applies for any kind of performance. It applies for grades. It applies for business. It applies for, I don't know, whatever you want, right? Anything that you want to pursue, if you keep doing that, if you keep trying again and again, and you keep making mistakes and you keep learning from those mistakes, you keep doing that, you can achieve whatever the hell you want. You can, you can also become Elon Musk if you keep doing that. That's exactly what he does. Elon Musk. He keeps doing it again and again and again, and trial and error, trial and error, trial and error. He keeps doing that very quickly. The process of, repeating and learning from mistakes is very fast. Elon Musk is one of the most, you could say, he has a very maniacal sense of urgency to do mistakes and then quickly learn from them. That's exactly why, he's faster than NASA in sending rockets and, catching them from air. Great guy to learn from, although some things, not all. But yes, okay. Sounds good. Take care. Allah Hafiz. I will see you on Wednesday. And on Wednesday, we're going to start work power energy.
Allah
Okay.
Hafiz.